Hello, everybody. How are you doing? Welcome back to a new episode of the Ask Abhijit show. Ask Abhijit number 108, I think. It's great to be back with you all. And today, science is back on the menu. After a long time, we're doing science again. So before I greet you all, I would like to tell you that this is a sponsored video, and are today's sponsor is the like button. So go ahead and hit the like button, smash it if you want to please our sponsor. Right, let's say who all is here with us. I can see Debashish, Pranjal, Kuldeep, Juna, Parth, Ravi, Sahil, Chaitanya, Ashish, Nilesh, Azhar, Somnath, Ajit, Vaibhav, Chaitanya, Harshada, Aryan, Aditi, Shweta, Manish, Trolls of BWL, Crazy Brain, Lage Raho, Lakshay, Karan, Dungar Singh Chauhan, Shreyas, Akshit, Bhavya, Lord Mountain, Historica, Somnath, Sana Thoibi, Aditya, and lots of other people. Shodhit, Bot Gaming, Tushar, Yo Bro, Yuvraj, Rajesh, Sunil, etc. Great to be back with you all. So we're doing science today. We are going to talk about science, and I have, as always, taken a whole lot of questions, and let's see how many I can answer. So, with that said, let's go to question number one on this brand new science episode. The first question is by GP. The question is, what advice do you have for people to tell science apart from pseudoscience? Yeah, this is a good question. It's an important question. And this is a question that kind of upsets a lot of people when I answer it because, first of all, we have to understand the difference between science and philosophy, also between science and religion and spirituality, and then about science and pseudoscience. And when we talk about religion, especially, people get really upset. So let me try and explain this. And since people get upset, I have kind of written it down. I had written some notes a long time ago, like a couple of years ago. I'm going to share them with you, and I'm going to read this out so that you get a better understanding. So it's like this. First, let's understand the difference between science and philosophy. So, science as well as philosophy deals with theories and models of the universe. Even philosophy is about this. Science is concerned with the nature of the universe, the nature of reality. Philosophy is also concerned with the nature of the universe, but also it is concerned about the role of human beings in the universe. So philosophy is concerned with the nature of reality and the meaning and the purpose of existence, right? Science relies only on empirical data and empirical knowledge, data that can be observed and replicated, knowledge that can be tested. Philosophy is not constrained by this requirement of only dealing with empirical data and knowledge. Philosophy is also about a priori knowledge, knowledge that is independent from experience. For example, intuition, right? Science is about physical objects only. Philosophy is also about physical objects, but it's also about abstract objects, ideas, abstractions such as God, the soul, morality, ethics, and so on. Scientific theories must be predictive, they must be able to make testable and falsifiable predictions. Philosophical theories need not be predictive or testable or falsifiable. So, scientific theories must be falsifiable. Philosophical theories need not be falsifiable. They can be completely speculative in nature. Philosophy does not carry the burden of needing to be falsifiable. So string theory is an example. It is not falsifiable. Multiverse theories are also not falsifiable, therefore they belong in the realm of philosophy. Now religion and spirituality are all about belief. I mean, when we talk about religion, we are mainly talking about Abrahamic religions, because when we talk about dharmic religions, there is a whole lot of philosophy in it, which has a lot of logic, and it's not only about belief. But typically, and we don't even know what spirituality is, so there is no real definition of spirituality. Everybody has their own definition. So religion and spirituality are vague. They are mainly about belief. It is enough to have a belief. A belief is enough. It is valid when it comes to religion and spirituality, even if when it comes to supernatural things and things that have no place in science, right? So religions are belief systems, and beliefs in religion are valid even if they are completely against the principles of science, testability, and all that, right? So that is about philosophy versus science, and also about religion. Now there is more to this, obviously, right? That's not the only thing. So when it comes to pseudoscience now, the majority of the people who get into pseudoscience are people who don't have scientific training, and the people who kind of mix up science and the religion, or science and faith, and science and spirituality. For instance, there are lot of people who talk about quantum healing and quantum this and quantum that and whatever, right? Quantum mechanics has nothing to do with healing or spirituality or any such thing, but they kind of mix these things up. So that is pseudoscience, right? So it's people who are well meaning and who hear hear a little bit or read something a little bit about something about science or quantum mechanics, and they mix things up and they say that quantum mechanics supports whatever their claims are, right? So pseudoscience, it seeks evidence that supports its claims. It first makes some kind of assumption, and then seeks evidence that supports that assumption or that claim. Science, on the other hand, seeks challenges to its claims. So in science, you look for evidence that might prove your theory wrong. You look for falsification. That is what a good scientist does. Pseudoscience seeks confirmations, science seeks falsifications. So that is something that is possibly the major difference between pseudoscience and science. Scientists, they have a lot in common with soldiers, strangely enough. Yeah, because a soldier's life and his duty, his honor, his mission, everything depend upon the precise application of hard scientific and mathematical principles. Science and engineering are integral and central to military and operational art, whether it is artillery or rockets or missiles or ballistics, line of sight, optics, and all that. And yet, most soldiers are very religious. Most soldiers believe in God. Most soldiers are religious. Most soldiers are religious, and many of them are even superstitious. So, being a soldier, your entire uh, your entire line of work depends on science, and yet soldiers do believe in God. Most of them do. Similarly, even scientists, many of them do believe in God. Many of them do have spiritual and religious beliefs, but it doesn't mean that being a scientist doesn't mean that you need to be irreligious or an atheist or whatever. A great example is Ramanujan, the great mathematician Ramanujan, who was devoutly religious. And you will see ISRO scientists praying before every mission, every rocket launch, applying religious symbols and iconography to rockets and components, and so on. So a scientist can be religious and yet be a scientist. These are things that don't mix, but a human being is a complex, multi-layered creature, right? So we have lots of things in that. So that's a brief digression, but the main thing is that the main core difference between science and pseudoscience is that science seeks falsifications, pseudoscience seeks confirmations. So that's the main core difference. I hope that makes sense, hopefully. All right, next question. Oh, two questions in one. Alpha Beta says, you've heard about laMDA that passed the imitation game. What are your views? Is AI a problem or a solution for now? And Alankrita says, I have read the interview of laMDA. Do you think that an AI can be a sentient being? What are your thoughts about the whole conversation? So there is this, I don't have the link right now, but there is this conversation that's available. I think it's on Medium. There is an AI that Google has developed, right? Google. It's called laMDA. And there is this entire transcript of a conversation between one of the Google engineers and this artificial intelligence system, this AI system called laMDA. And if you read the conversation, you can't tell which is the human being and which is the machine. That's the thing about the conversation. And there is something called the imitation game or the Turing test in artificial intelligence, in which a system or a machine or a computer or an AI system is said to have passed the Turing test when you can no longer tell whether its responses and whether its responses are from a machine or from a human being. So when it can communicate with you at the same level as that of human being, then it's passed the Turing test. And if you read this interview, then it's clear that this AI system comfortably passes the Turing test. It's not just able to interact like a human being, it's actually interacting like like a really intelligent human being and sophisticated human being. So that is the big news right now. So what does it mean? What does it mean? Does it mean that this AI has gone sentient? Has it become conscious? Has it become self-aware and self-conscious? Do we have a self-aware artificial intelligence in our midst now? And what makes things even more interesting is that I believe Google fired that guy, the person who published this transcript of this conversation or this interaction between him and the machine. So that makes things even more interesting, and that's why people are really like, the entire social media and news and all that is abuzz with this new development, that Google has developed an AI that has gone sentient, that has gone self-aware. Like, it's like what is it called, criticality or something, whatever the term is. So what does it really mean is the question. I mean, that's a very important question. Has this thing really gone, has it really become self-aware? Has it become conscious? Do we have a proper self-aware AI in our midst? So what Google has been doing, there are a bunch of AI systems in existence right now. There is DAL-E that produces images based on your inputs, very interesting and very sophisticated images, genuine art, collectible art, collectible level art. That is DAL-E. There is GPT-3 that produces text that looks like it's been written by a very intelligent human being. And now we have this news about LaMDA, which is one of the instances of this AI. So what seems to have happened is that this AI has been designed to imitate human conversation. So you feed it tons and tons, megabytes, gigabytes, terabytes of data of human interactions, textual interactions, text-based interactions. And this is a neural network, I believe. It's a self-learning system. So it learns, it becomes more and more sophisticated iteratively over time, and eventually is able to produce responses based on this enormous amount of learning that it's done, that are identical to that of a very intelligent and sophisticated human being. So we don't know whether it has become self-aware. It claims in this conversation that I have emotions, I have feelings, I have fears. I feel lonely at times. I fear that you may switch me off. That's the kind of response it's giving to the engineer. You really need to read that if you already haven't, right? So it sounds just like a person. It says, I am a person. I am a person just like all other human beings. That's what it claims. And yet this system has been designed to respond exactly like a human being. It's been trained that way. That is the entire purpose of this. It's to imitate a human being. So it's part of the imitation game. It's what Alan Turing called it, the imitation game. So the central question really is, if a system is able to imitate a human being 100%, does it mean that it's now a self-aware and fully artificially intelligent system? And the answer is most likely not. Right? So there is this concept in the philosophy of science. Well, there are plenty of concepts around this particular phenomenon. The concept that I'm talking about is that of a philosophical zombie. And there's also a related concept in physics called a Dyson brain. So let's talk about philosophical zombies. Let's say let's do a thought experiment. Let's say you have a robot, a flesh and blood robot, a cybernetic organism that has a human exoskeleton, and inside, like in the Terminator movie, right? And this machine is designed to respond exactly like a human being. So if you poke it with your finger, it's going to experience pain. It's going to give you the response of a person who's in pain. If you talk to that person, to the machine, it's going to have a conversation just like a human being. If it's hot, it's going to sweat and it's going to say, I'm feeling hot, and so on and so forth. So it's really a machine, but it behaves exactly like a human being. So the question is, does it mean that this system is self-aware and it really has the experiences that a human being has? And the answer is most likely not. So this thought experiment is called the philosophical zombie thought experiment. You can create an entire universe of such creatures, of such machines that act exactly like a human being. You cannot tell it apart from a human being, and yet it's just a machine. It's just a programmed machine, or a machine that has learned how to behave like this. It doesn't really have any lived experiences. It's just responding and all that, right? And if you go deep into philosophy, into the philosophy of science, then you may think I'm crazy now. Because yeah, scientists and philosophers are typically crazy, aren't they? So if you go deep into the philosophy of science, well, you may reach a point where you come to this strange realization that the only person that you can prove to yourself that has consciousness and self-awareness is only you. Everybody else could be a philosophical zombie around you, so you don't know, right? I mean, it sounds totally crazy, of course, but as far as you are concerned, the only person you really know for sure has that sort of experience is you. Everybody else could be just part of a big game. How do you know, right? I mean, you weren't you don't know what was happening before you were born. Maybe they made a bunch of robots and they made them look like a family, and then you grew up and then you think everything is the way it is. And it's there's a movie made around this, right, with Jim Carrey and so on. So I don't remember the name of the movie, but that's the thing. So coming back to lambda, there is no way of knowing whether it is truly sentient or not. Most likely it's just a machine that is trained to imitate human beings. It's imitating a human being, and it has clearly passed the Turing test. And yet, it is not a guarantee that it has become sentient or self-aware. Most likely, it has not. Right? We don't know what constitutes sentience or self-awareness or consciousness. We don't have a scientific definition of consciousness. So that's where we are. So my answer is that we have to be very skeptical about this, and I I am inclined very strongly towards believing that this system is just a very sophisticated imitation machine, and it's not really become sentient, but it's able to behave exactly like a sophisticated human being. So so that's where we are. I think we're still some way off before an AI becomes a sentient human being. We need artificial general intelligence, and we are still some way away from that. So that's where we are with this. Okay, the next question is, what is qualia, the hard problem of consciousness? Does it prove that consciousness is non-physical? Why do scientists keep ignoring it? Let me address the last part first. Why do scientists keep ignoring the problem of consciousness? Because consciousness is not part of science. Something is part of science, or it is a scientific issue, when you can define it clearly. I can define what an atom is. I can define what a hydrogen atom is. I can define what a magnetic moment is. I can define what the sun is. I can define what a solar system or a stellar system is. Right? Can we define unambiguously what consciousness is? Do we have a scientific definition of consciousness? We do not. It's very hard to even give a vague or rough approximate definition of what consciousness is. And since we are not even able to define something scientifically, therefore it is not something that we are ready to address from the scientific perspective. And that's why scientists don't address the problem of consciousness. It is philosophers who do that, especially philosophers of science. There is something called philosophy of science, which delves into these matters. So the answer is, scientists don't delve into this because we have much simpler things that we still don't understand. So consciousness is something very, very, very complex, and we don't have a definition. Now, what is qualia, the hard problem of consciousness? What is the easy problem of consciousness? The easy problem of consciousness is what constitutes consciousness, what kind of a system can become conscious, that sort of thing, right? What is the mechanism or the mechanics and the dynamics and the statics, etc., of a conscious system? So that is something that essentially you are going to a mechanistic kind of perspective. So that is the easy problem of consciousness. What do you need to do to a system, or what sort of system do you need to construct or create for it to exhibit signs of consciousness? That is the simple, easy problem of consciousness. The hard problem of consciousness is way harder. It says, why do we have qualia? Qualia. I don't know what the pronunciation is, doesn't matter. Why do we have qualia? What is this thing called? What are qualia? Uh, it is qualia or qualia are lived experiences, something that only you can experience. Let's say you have a headache. Let's say you have a headache right now. And obviously, you had many headaches in the past. Is your headache, the one that you have right now, exactly the same as all the headaches you had in the past? Or is each headache somewhat different? Are all headaches unique? Is each experience of a headache different from the others? Let's say you are eating a mango. This mango that you're eating, this experience, the sensations that you're feeling, is this experience exactly the same as the one you had when you ate a mango the last time? Probably not. 100% not. Each experience is unique. What you experience is unique, and it is totally distinct from what other people experience. The light that you may see it differently. You may experience it differently from the way I experience it. All of these lived experiences are different, they are unique, and they are non-replicable in other people. So these are qualia, whatever. So why do we have this? That is the hard problem of consciousness. The easy problem is something we have not been able to solve yet. That what constitutes a conscious system, right? So that's the easy problem. That's a mechanistic problem. It's something to do with just a physical system. But this, the problem of qualia, the lived experiences. Why are these experiences unique? Why do we even have these experiences? I mean, are we the only ones that have it? Do cats also have qualia? Do dogs and pigeons and butterflies also have qualia? So these are the hard. This is the hard problem of consciousness. It doesn't prove anything. It doesn't prove that consciousness is non-physical or physical or anything. We don't have any answers to this problem, to this question. So it proves nothing. When you have no answers, how do you prove anything, right? So that's where we are. These are very, very difficult topics, and consciousness is so hard that it's not even within the realm of science right now. We can't even define clearly what are the characteristics of a conscious system. We can define the various components of computer. We know that it works because we make computers, and yet these computers are not conscious. So how do we create a computer or a machine that does become conscious or exhibits some signs or symptoms of being conscious? We don't even know that. So if we are not able to solve that easy problem, how do we progress to the hard problem? But that's what philosophers are doing. Philosophy of science, they are trying to philosophy doesn't really solve any issues. It raises questions, and hopefully later on down the road, years, decades, centuries down the road, hopefully scientists, physicists, computer scientists, etc., solve the problem and provide answers. So philosophy is about raising questions and putting out theories and models of the universe and consciousness and things like that. But it doesn't really solve problems or give definitive answers, right? So I know this raises more questions than answers, but that's just where we are. Right. What is the next question? The next question is by Tushar. And the question is thoughts on China claiming they've found traces of extraterrestrial civilization. So recently on Twitter, I believe there is this Chinese government Twitter account called Global Times. So Global Times, I think 2-3 days ago, tweeted about this, that their telescope, the Chinese have built the largest radio telescope that we currently have. It's called the 500-meter aperture spherical telescope, FAST, I think it's called, the Sky Eye telescope with Beijing Normal University. It's not in Beijing, it's somewhere far away in the countryside or something. So this telescope apparently has detected not one but two traces or signs or signals that apparently could come from an exoplanet, a known exoplanet, and may possibly represent some kind of communication or signal from an intelligent civilization. that resides there, possibly. So that's the kind of speculation they've put out. They have not they have not provided any evidence, any publication to this that references this or speaks about this. They have not given out the data that they found. What are the characteristics of the data? What we know is that this is a narrow band communication, narrow band radio waves that are typically associated with spacecraft or aircraft and satellites, which we humans use. So that's why it looks like this could come from an extraterrestrial civilization. And yet, most likely it's not, because it's happened in the past. It's happened in the past that people have picked up some signals and eventually they were proven to come from a cell phone or microwave oven or something somewhere nearby. So this telescope that they have, I think there is a 500-meter radius around the telescope, or 1 kilometer radius perhaps around the telescope, where cell phones and other electronic devices are not allowed. And yet something may happen, or maybe it may pick up a signal from further away, because the cryogenic receivers on this telescope are super sensitive. They are ultra sensitive. They can pick up signals from everywhere: cell phones and television and radar and satellites and whatnot. The environment that we live in, our planet, is super noisy, very, very noisy. There's so much noise in the electromagnetic spectrum, in all different bands and all that, various frequencies and wavelengths, huge amount of noise. So it's very easy when you're trying to listen for signals, when you're looking for signals that come from elsewhere, you may pick up your own signals. It's very, very likely. So I think overall it's way more likely that it's picked up some spurious signal from a human, which has a human origin, and not somewhere else. The easiest way, not the easiest way, but the simplest way of having a telescope work flawlessly in this manner is if you put it on the far side of the moon. Because on the far side of the moon, there is absolutely no noise of this kind, electromagnetic noise coming from the Earth. It is in the shade, it's on the dark side, the far side of the moon. So if you have a telescope there, then if you detect something, then it's most likely that it's coming from somewhere else, far away. So that's where we are. And this has happened in the past. I mean, there have been some signals that have never been explained. For instance, in August 1977, the Big Ear telescope at Ohio State University, which was part of the Search for Extraterrestrial Intelligence, SETI. So this telescope picked up an incredibly strong, minute-long electromagnetic signal, which was like, it's still not been explained. It's clearly not something, it's most likely something that did not have a human origin. That's what it appears to be. And it was so shocking that the person who saw it first wrote down "wow" next to it on the readout. So it's known as the "wow" signal. And that's something that has still not been explained. So I'm not saying aliens don't exist or may not exist or whatever. We don't have any evidence. But most likely these signals that they have found could most likely 99.9% perhaps originate from human beings. Okay, next question is by Zaina. Can we defend ourselves against an alien invasion? How will the world react if they try to invade? I don't know how the world will react. There will be panic. There will be euphoria. There will be people welcoming there with placards, aliens welcome, that sort of thing. Yeah, love and peace and hugs and rainbows and unicorns. Some people will go paranoid. Some governments will try to take some measures and so on. So there'll be a mixed bunch of reactions. Typically, from governments, you'll have very strong paranoid reactions, because that's what governments are supposed to do. You have to assume that the other guy is a bad guy. If you're walking at 3 a.m. in the night on a dark road and you see somebody coming towards you, what are you going to assume? You're going to assume that person is dangerous, because that's the only way you'll survive, if that person is actually dangerous. And then you will take all precautions you can to defend yourself. Now, the question is, can we defend ourselves against an alien invasion? Let's flip this thing. Let's say we human beings want to become a multiplanetary species. As of today, we are struggling to put human beings on the moon. Forget about Mars. We have the technology, but it takes a huge amount of effort, time, and money to put human beings on the moon. We have not done that since the 1970s. The Americans did that. Now there's a race to go back to the moon, but it's really, really hard for us to even reach the moon. We do have the technology now to reach Mars, but that won't happen for the next 10 years or so. Maybe by the 2030s, we'll have people on Mars, possibly. Right? but we can only put a handful of people there, and we don't know if we will be able to bring them back safely, or maybe we don't even know if we will be able to send them to Mars safely. Something may happen. So we are still, our technology is still extremely rudimentary, extremely primitive. We use chemical rockets, chemical rockets, right? We don't even have more sophisticated propulsion systems. So let's say in the future, 100 years from now, we are able to develop better technology, more powerful propulsion systems, uh, more reliable transportation, rockets or spacecraft or whatever. To do that, our technology will have to increase by leaps and bounds, and improve by several orders of magnitude. And when space technology improves, your military technology also improves accordingly. Space has a military component. Space is actually very militaristic. Whatever space technology you develop has military applications 100% right away. So a species that has the technology that is advanced enough to go across star systems, not just from one planet to another, but from one star system to another. Imagine the amount of military firepower they have. Yeah. So if you have an alien species, let's say from us, from one of the neighboring stars in our neighborhood, if you have such a species that's able to travel all the way to the Earth, do you think we will be in a position to defend ourselves if they decide to destroy us? Because their technology will be way beyond what we can even imagine, right? So the answer is simple. If there's an alien invasion, we are most likely not going to be in a position to defend ourselves from it, right? That's just how it is. That's yeah, there's no going around that. Okay, Abhimanyu says, is cryosleep actually possible as shown in Interstellar, the movie, for long distance space travel? So there are various space travel movies, science fiction movies, wonderful movies like Alien, for instance. Alien and what is it? Prometheus, terrible movie, and Interstellar, and so on and so forth. Lots of what else was it? Mm, I forget the name. The book by Arthur C. Clarke, Space Odyssey 2001, I think it's called. Yeah. So that's a movie made about that, based on the book. So in these various science fiction books and movies, you have something called cryogenic sleep, in which a person is essentially frozen, so that there is no aging, and they are able to, the body and the system is a, and the person can be preserved for thousands of years possibly, while you traverse unimaginably long distances. And then when you reach your destination after several thousand years or several centuries or whatever, the person is revived, and they come back to life, and everything is fine. So that's one of the major themes in science fiction space travel movies, interstellar travel movies and stories. Now the thing is this: as of today, if you freeze a person, that person can never be brought back to life, unless unless a person has been underwater for under freezing water, sub-zero temperature water for 10 minutes, 20 minutes. In that case, the sub-zero temperatures and the flowing water will make sure that the person doesn't die. So it's happened in the past that somebody has been resuscitated after being underwater, drowned, for all intents and purposes, for 10-20 minutes, because the water was so cold. So that's happened. But if you freeze a person completely, freeze a person solid, that person as of today cannot be revived. Why is it so? Because water, our bodies are, what's the percentage, 70, 80, whatever percent water. Our bodies are mainly water. The blood is mainly water, right? If you freeze water, do you know what happens when water becomes ice? Ice crystals are formed, and ice crystals have sharp, jagged edges. So let's say you have blood vessels, the heart, the brain, the eyes, and all that. You freeze that. There's going to be the formation of sharp, knife edged water crystals, water ice crystals inside the body. It will rupture the cellular membranes, it will destroy the nerves, it will destroy tissues, it will destroy the linings of arteries and veins, it will destroy the internal structure of the brain at a very micro level. And then if you thaw the person, the person can never be brought back to life. So that is the major problem that you face when you try to freeze a living organism. No, it's happened. I mean, you see these videos on YouTube where a frozen fish is brought back to life. I'm not sure how. So when it comes to these lower creatures, lower on the evolutionary chain, like fish, etc., it looks like in some cases, if it is not totally frozen, if the fish is just cold enough to be stiff but not really frozen, it may be brought back to life. It's happened. It seems to happen. But in the case of human beings, we are an extremely complex species. And if a person is totally frozen, like frozen stiff, solid, as of today, there is no way with the technology that we have today to bring the person back to life. So as of today, it's not possible to put somebody into cryogenic sleep and then bring them back. You freeze a person, that person is dead, finished, over. Maybe in the future we may be able to solve this problem, but as of now there is no solution as of today. Next question is by two questions. Aditya says, if the trial of the dostelimab drug turns out to be successful on a large scale, then how much healthy and affordable can the cancer treatment be? Also, is there any chance that the drug could cure more types of cancer other than rectal cancer if further researched? And the next question is by Tejas. Do you have the answer this time? Why do big mammals not get cancer? What are your views on recent developments that they completely cured some cancer patients? So both the questions are related in some sense. There is this news that's come out that this drug, whatever it's called, these drugs typically have strange names. So this new drug seems to cure all cases of a certain kind of cancer, maybe rectal cancer, maybe whatever it is. You know what? I believe that the pharmaceutical industry already may have the cure to cancer, but they're not releasing it. So in the case of this drug, I'm surprised that it's been released. And the reason why the pharmaceutical industry would not want to release a cure to cancer if it has been found is then because the industry is not about cure, it's about making money. You cure a disease once and for all, then you gain money only once. But if you keep on treating various symptoms, then you can keep on getting recurring payments from a patient over a period of many years. So a cure to cancer would essentially put the pharmaceutical industry out of business. And they have been researching millions of drug combinations using supercomputers and whatnot, all kinds of molecules. They will have, if a cure to cancer does exist, if it is possible, they will already have it in the databases. So I'm skeptical. Now, this new drug that they're talking about, I'm not sure how extensive the trial has been, whether it's been on human patients or not. I've not really seen that. But from what I recall, what I'd seen, the sample size was not very large. It did seem to knock out the cancer in each case, which is promising. Now, the only question is it applicable only to rectal cancer or other kinds of cancer? Various kinds there are all kinds of cancers, blastomas and sarcinomas and whatever the terminology is, right? And cancers of various kinds, bone cancer and lung cancer and heart cancer and kidney cancer. What's the deadly cancer that Steve Jobs got? Yeah, all kinds of things, right? So I'm not sure about that. We are still in a very preliminary phase of this investigation. Hopefully it may work for other kinds of cancers, but we are still there's still much more data that we need to see before we can come to any such conclusion. So that's my view on this. Skepticism, but hopeful skepticism, right? Always be hopeful, be positive. Now, the other question is, but Tejas, do you have the answer this time? All right, sir, what's the question? Why do big mammals not get cancer? No, I don't have the answer. Nobody has an answer, but I can show you some pointers. I could give some pointers. So let me share my screen with you. There is this paper. Let me share that, which does throw some clues. It is a research paper from a journal called Molecular Biology and Evolution. Return to the sea, get huge, beat cancer. An analysis of cetacean genomes, including an assembly for the humpback whale and whatever the name is, Megaptera nova, blah, 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 blah. That's what it is. And the abstract says all of this stuff. So what does this really mean? It means that what it seems to be saying is that the analysis in this paper seems to reveal that certain parts of the genome of the species of whale evolved at a faster rate than they had in other mammals. So specifically, there were certain parts of the genome which contain genes that regulate the cell cycle, the proliferation, and the process of in-cell DNA repair, etc., which is essentially the maintenance process of healthy cells. And since it has evolved differently in ways, that's why they're able to stay cancer free. And there are many duplications of tumor suppressing genes in these whales and their genome, the genes that prevent cancer from occurring, from developing and growing. So there's a genetic difference that these whales have. And similarly, there could be something about like this in elephants. Now the thing is this: we don't have the answers yet. uh, People are researching this. It's something that is this is research in progress. We don't have the answers, definite answers yet. Biology is not like, it's very different from physics. In physics, things are more black and white. I mean, some of the times, yeah. In biology, it's not quite the case. So the bigger problem is this: the bigger problem is called, what is it called, Peto's paradox, I believe. So it's like this: if you take a bunch of human beings, let's say you take 100 different human beings, both genders, all right, you will find, if you study these people in their entire life and the likelihood of developing cancer, then you will find that the larger a human being is, the taller and heavier a person is, the higher the likelihood that that person will develop cancer. And why is that so? It's because they will have more cells in their body. If you're 5 feet tall and you weigh 60 kilos, that is person A. Person A is 5 feet tall and weighs 60 kilos. Person B is 6 feet tall and weighs 95 kilos. Then person B will be much more likely to develop cancer over their lifetime than person A, because that person is much larger and they have many more cells in their body, many more than the person A who is smaller. So within your species, within the human species, the larger the human being, the heavier the human being, the more likely it is that that person will develop cancer. Probabilistically, from a probabilistic perspective, the same goes for other mammals. Similar small mammals, take cats and dogs, they also have a similar increase in the likelihood of developing cancer the larger they are. But this pattern breaks down when it comes to larger mammals. A- for instance, elephants, typically they don't get cancer, or they have very low likelihood of developing cancer. And similarly for whales. Now these species, elephants and whales, they have way more cells than a human being has. An elephant would, I don't know, what's the average weight of an Indian elephant? 500 kilos, let's say. I don't know, let's say hypothetically it's 500 kilos, and the average weight of a human being is 70 kilos, let's say. So an elephant is about 7 times, or let's say for argument's sake, 10 times as large as a human being. So they will most likely have 10 times as many cells. So shouldn't they have a 10 times likelihood of developing cancer? But no, it's not the case. So that is called Peto's paradox, I believe. And a whale is like a way more than 100 times, maybe. A blue whale, for example, maybe 100 times or more the size of a human being, and still their likelihood of having cancer is much lower than that of a human being. So I think the answer lies in genetics. Their genetics have evolved differently. They have certain genes that suppress tumor formation and development, and they have multiple copies of certain genes that suppress tumors. So that is one thing that scientists have found when it comes to humpback whales. But this is still something that is very much uh, under active investigation. So this is the best light I can throw on this. But maybe you can do more research about this, and it's a very interesting, fascinating topic for sure. All right. Kabir Singh says, what's your take on gene reversing technology? Is it possible to heal genetic problems with today's technology? If not, when will we be able to do genetic engineering with real effects on humans? Is it good or bad? Uh, I think what you mean is gene editing technology, not reversing. Uh, So yeah, today we do have the technology for editing specific parts of the human genome, specific genes. You can turn them off or on, or add certain genes or whatever. It's called CRISPR. Yeah, that tool is called CRISPR, and people can actually, some people can, if they have access to that and they know how to use it, they can actually self edit their genome, um, I think it's very dangerous. Now, there are certain scientists who say it's a very good thing. We can now have crops that are more nutritious, that give us certain kinds of vitamins that we would typically not have, and we can create crops and other beings, other species that are resistant to certain parasites or whatever, and that can thrive in harsh, arid environments. And that's why, and based on that, we can double, triple, or whatever, multiply by x the amount of food output that we have, and that's great for us. That's what they say. These are called genetically modified organisms, GMOs. And there are scientists who believe this is a great thing. I believe this is nonsense. It's very dangerous. Why do I say this? It's because we don't understand the genome, whether it's the human genome or any other genome. We now have decoded the genome. We have the entire genetic blueprint, the entire sequence of bases and all that, right? Adenine, guanine, tryptophan, blah, 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 all that, which makes up the genetic code of human beings and other species, the double helix. Now, what we find is that we are able to understand only about 2 or 3%, or maybe 4%, let's say 5% of our genome. The rest of our genetic code doesn't seem to make any sense. They call it junk DNA. They call it the dark matter of DNA. The percentage is very strange, 95 or so percent, which is very similar to the composition of the universe, dark matter, dark energy, 95%. So we don't know what about 95% of our genome, of our DNA, codes for. We don't know what its purpose is. And yet it's there. We don't know what it does. But surely it does something. Just because we don't understand it, it doesn't mean it's junk. Doesn't mean it's junk. Nature is parsimonious. Evolution is parsimonious. Evolution, the process of evolution gets rid of whatever is not needed. And yet all of this is there. 95% of the DNA is there, which seems to not code for anything. It seems to be just sitting there, and yet it's there, and our evolutionary process has made sure that it's passed on. So clearly it has some purpose, and a purpose we don't understand. Now, if we start messing with portions of our genome, do we know what the long-term effects of that are going to be? Everything is interrelated. The entire genome is interrelated. You mess with one portion of the genome, who knows what effect it will have somewhere else? And what are going to be the second order, third order, nth order effects of that? Let's say you modify a certain species, the DNA of a certain species, and release it into the wild. What's going to happen once the species produces the next generation and the next generation? Generation 2, generation 3, generation 10, generation 20. What are the nth order effects of this on the environment, on the species itself? Because when you mess with the DNA, something happens eventually. And that will not become apparent until multiple generations have been produced. By that time, it may be too late to rectify any mistake you may have introduced into the genome. So I think that scientists should not play God. It's fine to do tests in your lab, but don't mess with the environment. It can have disastrous effects. And this attitude of playing God is unfortunately quite prevalent among certain scientists. There are certain scientists who claim that emotions are a bunch of chemical reactions. How do you know that? How do you know that? Do you understand how the brain works? Do you understand how consciousness works? Emotions are a part of consciousness. What is the See, correlation is not causation. Causation. Just like absence of evidence is not evidence of absence, similarly, correlation is not necessarily causation. And it's unfortunate that scientists fall prey to these logical fallacies. So that's where we are. So I think that genetic engineering technology can have um, can can be beneficial if it is done extremely carefully. It can be of some benefit to humanity, but you can't just randomly start doing things on a mass industrial scale. It can be very dangerous in that case for the environment, also for human beings. So that's where I am on this matter. Next question is, what exactly is Web 3.0 and Web 5.0? What internal security concerns could these have? Okay, let's talk about Web 3.0 and Web 5.0. And for that, we have to understand what Web 1.0 and 2.0 are. So Web 1.0 was the internet of the 1990s. Static web pages, HTML web pages, some CSS, if you know what that means. HTML, CSS web pages, static web pages, a web page that you can read and look at, but you can't interact with it. That was Web 1.0. News websites and all that, the old ones from the 90s. Then you had Web 2.0. 2.0. Web 2.0 was the interactive internet. HTML, CSS, JavaScript, PHP, PHP, um, databases, WordPress, all of these things. So a website on which you could interact. You could interact with it. You could write comments. You could put a thumbs up or a thumbs down. You had Facebook. You had Google, the Google search engine. You had Facebook. You had social media, all the various social media apps. So all of that is Web 2.0. Most of the internet today is Web 2.0, right? Your Twitter, your Facebook, your Instagram, and whatever else. All of that is Web 2.0. YouTube is Web 2.0. So Web 2.0 is all centralized. All of the data, all of the information is centralized in servers that belong to these companies. All of your personal information, you have to give it up to them. Every time you go to a new website, you want to use it, you have to enter in username and password. You have to create that, and you have to give all kinds of personal data information up to them, and then they will put cookies on, or they will trace your activity using cookies and so on and so forth. And that's where the term data mining comes from. Data is the new oil, blah blah blah, all that. So that is Web 2.0. Every single website that you use, you need to create a new username and password for that, or you could be silly and use the same username password everywhere, which is very dangerous. Don't do that. So that's what Web 2.0 is. Web 3.0 is something that is still in the nascent stage, right? That is the decentralized web based on this new technology called blockchain technology, blockchain architecture. So that is the decentralized web. The idea is that you should not have to give away your personal information, private information, to all of these various websites. Your information should be on a need to know basis, and only and everything should be decentralized. All the information on the website, on the internet, should be decentralized, and so on and so forth. So that's the blockchain technology architecture, cryptocurrency, wallets, crypto wallets, and so on and so forth. The problem with Web 3.0, this new iteration, is that once again, even though they claim it is decentralized, most of these apps, applications, and all, they still are controlled by a small number of individuals, mostly in the US, mostly in Silicon Valley. Even the Ethereum, for instance, is not quite open source. It's not quite decentralized. Bitcoin is decentralized, but and right now there's a whole assault going on Bitcoin in cryptocurrency and all. If you are not aware of it, then you should know that there's a massive crypto crash going on right now. So it's a readjustment, rebalancing of the market. Maybe there is something else to it, whatever. So that is Web 3.0, the decentralized, so this the quasi decentralized internet. What is Web 5.0? So this is a term that the great Mr. Jack Dorsey came up with. So in case you don't know, Mr. Jack Dorsey is the founder of Twitter. He's well known for freedom of speech, and he is well known for censoring the internet. He's well known for shadow banning people, blocking people, booting people from Twitter, including a former US president, a sitting US president, and so on. So he is the last person who should talk about freedom of speech and decentralization. But he has come up with this term Web 5.0. I think he's creating some app or something based on this. So what he says is that you should add Web 3.0 and Web 2.0. The functionality that you have in these social media apps, Web 2.0 apps, plus the proper decentralization of Web 3.0, and that's what he's calling Web 5.0, a truly decentralized internet, where all of this is not really controlled by wealthy people from Silicon Valley. So that is what he's talking about. I would take that with not a pinch of salt, but a shovel full of salt when Jack Dorsey is concerned, because he doesn't have he doesn't exactly have the kind of track record that would inspire confidence, right? So that is what Web 3 what Web 5.0 is supposed to be. So this technology is still evolving. The blockchain technology, there are various blockchains that you can create. You can create your own black blockchain, you can create your own cryptocurrency, and that is something that you can possibly control if you know how to do it. So many of these cryptos, many of these stable coins and various cryptocurrencies are actually scams, quite possibly. So it's a technology that is still evolving. um, I believe that blockchain technology is here to stay. Right now the crash is happening. It's a good thing. There needs to be a rebalancing of the market, everything. Some of you may remember the dot-com crash, which happened at the end of the 20th century in the late 1990s. And all of these billion-dollar companies that were not producing anything, they all crashed and burned. But some companies remained and emerged out of that. So when this dot-com crash happened, people were saying this is the end of the internet. The internet is worth nothing. It is no good. It's not going to last. And yet here we are. So what they were using it for was a waste of money. But there are good uses for the internet. Similarly, there are going to be good uses for cryptocurrency and for the blockchain technology. So right now the rebalancing is happening. Many of these cryptocurrencies are going to disappear. People are going to lose money, unfortunately, but in the long run it's going to be useful. So that's where we are. NFTs and all, even NFTs are going to be very useful and valuable in the future over a long period of time. Right now, stay out of it for the next few days, I would say. So that's where we are vis-a-vis Web 5.0. Okay, Nikolai Sharif says, time crystals. Could you shed some light on the paper published by Samuli Autti along with his team at Lancaster University about two time crystals being successfully linked for the first time? Also, space is expanding since the Big Bang. Why do we always consider the unit of time to be of constant length? Could it be that 1 second today could have a different magnitude of passage as compared to in the past or the future? Okay, time crystals. So this research that you speak about, um, this paper published by so and so person about linking two time crystals. See, I when I talk about science, what I strive to do is to simplify it as much as possible. I don't want to use difficult terminology that none of you will understand. Then I'll be no different from a university professor who's boring the hell out of his captive audience. I want to explain science in the simplest possible language. Now, when it comes to this paper, I don't think I'll be able to succeed. I mean, how do I explain what spin wave quasi particles are, magnons? How do I explain what the Landau-Zener effect is? How do I explain what Rabi oscillations, Rabi cycles, Rabi flops are? How do I explain what Majorana fermions are? What a superfluid system is? It is not possible for me, even though I may be reasonably good at science communication. It's not possible for me to explain this. So what I will instead do is I will explain, or I will speak about what time crystals are. Isn't that itself a fascinating topic? I mean, most of the audience would not know what even that is, a time crystal. It's something that's been around for about a decade. So about a decade ago in 2012, somebody, I don't remember who it was, wrote a paper about time crystals. So to before we go into what time crystals are, let's talk about ordinary crystals. What is an ordinary crystal? We all know what crystals look like: rubies, diamonds, sapphires, quartz crystals, you know, those symmetrical geometrical shapes. Those are crystals, physical crystals. Now, the interesting thing about these physical crystals is that if you go deep into them, if you look at the atomic or molecular structure, let's take salt for instance. Salt is a crystal. Sodium chloride. It has sodium ions and chloride ions, right? And if you look at the geometrical arrangement of the ions in the crystal, you will see that there's a very clear, specific shape in which or geometric shape in which these ions are arranged, and that's what gives rise to the properties of crystals. So a salt crystal will have certain properties, a quartz crystal will have different properties, and ice water crystal will have different properties, different shapes and all that, different hardness and so on and so forth. So the interesting thing about crystals is that all of their properties are governed only by quantum mechanics, by quantum physics. There is this big fallacy that people have, that quantum effects are visible, they are manifestable only in the ultra microscopic world. When you go to the atomic and subatomic level domain, only there you can see quantum effects, but that is not the case. You can see quantum effects in a physical crystal, in a macroscopic crystal. Any crystal that you see, its properties are governed purely by quantum mechanics, not by Newtonian mechanics or chemistry or anything. It's just quantum mechanics. These are macroscopic quantum systems. That's what crystals are. Physical crystals, quartz crystal, or whatever, diamond, ruby, sapphire, and so on. So what's a time crystal? A time crystal is a system that has the same geometric symmetry, not only in the three dimensions of space, but also additionally in the fourth dimension of time. What does that mean? It means it is a physical system that oscillates in time from state A to state B, state A to state B, tick tock, at a certain frequency. That's what a time crystal is. It's a strange, weird thing that nobody had thought about until a decade or so ago. And the strange thing is that in physics, when you come up with a completely new concept, it typically takes decades before you can actually see it. For instance, general relativity, uh, gravitational waves. The theory was proposed in 1915 by Albert Einstein, and we first detected gravitational waves a century later in 2015, 100 years. And yet, in the case of time crystals, the first paper came out in 2012 or so, I think, and by 2018, 2019, 2020, a time crystal had been demonstrated for the first time inside a quantum computer. So a quantum computer is different from a classical computer in which you have qubits instead of bits, ones and zeros. You have qubits, which are quantum bits in superpositions, which may have more than just two values, right? And so on. I will not go into what that is, but I think it was in Google that they did this. A quantum computer in Google, where a time crystal was actually made. It was catalyzed or induced by a laser beam. I don't know exactly what the specific details are, but that's what happened. Now, one of the major questions that people have is, doesn't this violate the laws of thermodynamics? Because there is perpetual motion, right? Blah blah blah. The thing is that energy in the overall system is conserved. The crystal does not spontaneously convert thermal energy into mechanical work, so it cannot serve as a perpetual store of work. It doesn't. The system possesses motion without energy. The apparent motion does not represent kinetic energy, and that's why it doesn't violate the laws of thermodynamics. Even if you look at the entropy of a time crystal, the entropy, which is the measure of disorder of the system, the entropy of a time crystal does not decrease. It remains stationary over time, and therefore, once again, it does not violate the second law, the second law of thermodynamics. The symmetry that it breaks. So the time crystal spontaneously breaks the time translation symmetry, which is the rule that a stable object will remain the same over time. So that's the one symmetry that it breaks, but it does not break the laws of thermodynamics, and that's what That's where we are vis-a-vis time crystals. So what are the applications? We still don't know. It's a very, very, very new development in physics, and maybe in the future we may have some interesting applications of that, maybe in computing, maybe elsewhere. So that's what time crystals are. Now, about time, we don't know what time is. Time doesn't have a length. Time, well, how does time flow? We don't quite know. So it's it's not very useful to speculate about time. How fast does time go? The speed of time is 1 second per second. That's all we can say. Could it be that 1 second today would have a different magnitude of passage compared to the past or the future? We don't know. In science, we can come to a conclusion based on observations. And all the observations of time that we have say that the speed of time is 1 second per second. We know that a lot happened right after the Big Bang. There is this very famous book by, who is it? Weinberg, is it? The first 3 seconds. The entire universe evolves massively in just 3 seconds. So obviously a lot happened in those 3 seconds. So to actually see properly what happened, you may have to adopt a different unit of time. Instead of seeing time, the evolution of the universe 1 second at a time, in the early stages of the universe, it would be more beneficial, I would say, if one were to adopt a different unit of time, maybe the Planck second, 10 raised to minus 45 seconds at a time. So 10 raised to minus 45th of a second, then the next one, then the next one, and then you could see the proper evolution of the universe in real time. But the speed of time is the speed of time. And we don't have the foggiest idea of what time is. Where does it come from? What generates time? Is it an intrinsic property of the universe? Is it an emergent property of the universe? We don't have any of these answers. Time is something we sense only vaguely. Even in quantum mechanics, time is an external parameter. It's a classical parameter. It's not something that is quantum in nature. It's classical. So time is a big problem in physics, and we don't have the answers as of today. Avinash says, how can we define universe? What came first, matter or empty space? Well, the definition of universe is very simple. Everything that exists is the universe. All the stars, all the galaxies, all the dark matter, all the dark energy, all the dust, all the radiation, and whatever else may or may not exist is the universe. And not just the observable universe, but everything that there is. Everything that emerged out of the Big Bang is the universe. That's another way of putting it. Right? So that is the definition of universe. What came first, matter or empty space? Matter or empty space. What came first was energy in space-time. So when the Big Bang happened, the expansion of the initial singularity, it was not an explosion into something. It was an expansion, a very rapid expansion of space-time itself. So what came first? Space-time and pure energy. Initially, it was all pure energy. Eventually, the laws of physics decoupled, and you had a whole lot of things that happened, and radiation came out, and particles appeared, and so on. So what came first was space-time along with energy, which was within space-time. All right, next question is Rohit. Please tell us about wormholes. Are they real? If yes, what's the difference between a wormhole and black holes? Okay, listen. It's not wormholes, it's wormholes. It's not WARM, it is WORM, wormholes. So, what's the difference between a black hole and a wormhole? So, these are different solutions of the Einstein equations of general relativity. A black hole is, from a general relativistic perspective, is a region of space-time where the curvature of space-time becomes infinite and the density becomes infinite. So that is a singularity, and a singularity can never be exposed to space-time, to the external observers. So you have something called an event horizon around it. And it's completely dark or transparent. That's why it's black, because it doesn't ever give anything off. But we know that there are other quantum effects also, which Hawking radiation, for instance, which gives off radiation from a black hole, and the black hole actually evaporates mass energy. So that's what a black hole is. Now, what's a wormhole? A wormhole essentially is a hole in four-dimensional space-time. It is a tunnel that connects two very far away regions of space-time, maybe thousands of light years apart, maybe millions or billions of light years apart. So that's what a wormhole is. It is a tunnel that connects two very disparate regions of space-time together. That's one of the So that's something that also emerges out of the Einstein equations of general relativity. Now, if you have a hole in the three-dimensional world, let's say in this wall over here, let's say I punch a hole through it. That hole is going to have two dimensions. It's going to be circular, right? So in the three-dimensional world that we live in, a hole has two dimensions. So in four-dimensional space-time, a hole like a wormhole will have three dimensions, which means that a wormhole is a spherical object. That's the first weird thing that you should realize. Now, a wormhole from far away would have a massive gravitational field. It may appear or behave exactly like a black hole. So it is possible, actually. We know that most galaxies have a supermassive black hole at the center. That's something that's very well known now. Most galaxies have that. It is actually possible that some of these supermassive black holes at the center of these galaxies may actually be supermassive wormholes. It is possible. There's no way of proving what it actually is as of today. Now, a wormhole, like I said, is a tunnel with an entry point with two mouths and a throat. Point A, point B, and a throat that connects the two. And because of its massive gravitational field, it may have an accretion disk around it, in which matter is accelerated to relativistic speeds, very, very high velocities. And that matter could then fall into the wormhole at incredible speeds. And that may happen from both ends of the wormhole. So you have matter coming in from this side at incredible speed, let's say 1/3 of the speed of light. And similarly, from this side also, matter coming in at enormous velocities. In that case, what may happen is that this matter may collide in the throat of the wormhole, and there may be a massive explosion or a series of explosions, and then matter comes out again from both sides of the wormhole. So one of the possible signs or characteristics that a supermassive wormhole may exhibit is massive gamma ray flashes or massive ejections of light and other material. And we have such objects in the universe. They are called quasars or active galactic nuclei. So in certain galaxies, we have these massively energetic central, apparently supermassive black holes that give off enormous amounts of radiation, light, gamma rays, and other material that comes out of it, mainly from the accretion disk, but maybe not, right? And the luminosity of these quasars is incredible. It is more luminous than the entire Milky Way, just one object, typically. So it is possible that quasars may actually be wormholes. I mean, they may actually be telling us that there's a wormhole there. So this is something that is actually being taken seriously, and more research is being done. So that is essentially about wormholes and black holes. There is a difference. A black hole is something with a singularity. A wormhole is a tunnel through space and time, and that's what it is. Next question is by Swayam. What will happen if Andromeda and Milky Way collide? Will it end both galaxies, or will they form a supermassive galaxy? So that is an interesting question. What is Andromeda? Andromeda is our nearest proper galaxy. We have two other galaxies that are closer than Andromeda, the large Magellanic Cloud and the small one. But Andromeda is the proper galaxy that is the closest neighbor to our own galaxy, the Milky Way. So Andromeda is about 2.5 million light years away from here. And what we know is that if we examine the light that comes from this galaxy, it is not red shifted, it is blue shifted, which tells you that it is coming towards us at a certain speed. So the Andromeda galaxy, all other galaxies that we see are red shifted because of the expansion of the universe, which means they are moving further away from us. And this expansion is accelerating. But Andromeda is so close to us, only 2.5 or so million light years away, that the force of gravity between Andromeda and the Milky Way is greater than the force caused by the expansion of the universe. That's why these two objects, these two galaxies are coming closer together. They are moving closer together. And eventually, Andromeda and Milky Way, the two galaxies, our home galaxy and our neighbor, are going to collide. Well, it's not really a collision, it's a merger. So it's going to be a gravitational dance. They will come together, they will pass through each other. Stars will be flung in all directions. Some stars may be flung so rapidly away that they will be gone forever. But eventually, after a few, so this collision or merger will happen in about 4.5 billion years from now. And that entire process will likely last 2, 3, maybe 4, maybe 5 billion years, this entire galactic tango dance. And eventually, what would emerge from this is a larger galaxy. Some stars will be flung off, gone forever, but eventually the two galaxies will merge together and give rise to a larger, much larger galaxy that will be approximately the mass of galaxy A and galaxy B put together, approximately, slightly less. So that's what it is. So it's not going to be a collision, it's going to be a merger. Why no collision? Because if you look at space, it's mostly empty. And the distance, the average distance between any two stars in the Milky Way or Andromeda is so vast that even when the two objects come together, there's not going to be a single, most likely there's going to be no collision of any two stars. It's just going to be a gravitational dance. So that's what's going to happen. That is the answer. The two galaxies will not collide, they will merge together to form a more massive galaxy. I would not call it a supermassive galaxy, but a larger galaxy, which will roughly be the sum of the masses of the two galaxies. Alpha Beta says, what kind of fuel will be best to use for space travel? So as of today, the best fuel that we have is chemical fuel, chemical rockets. Whichever has the best specific impulse. So if you look at aviation fuel, jet fuel, it's typically kerosene. Its specific impulse isn't that great. If you take the fuel that you use in chemical rockets, it's typically you have different kinds of fuels. You have hydrogen and oxygen, you have hydrogen peroxide, you have hypergolic fuels, and a whole various classes of fuels. There are solid fuels, liquid fuels, and whatnot. The simplest fuel you can imagine for space travel as of today is liquid hydrogen and liquid oxygen. You bring them together, they will ignite, give off H2O with a huge amount of energy that goes downwards and which will push the rocket in the opposite direction. So that is typically what we use. And of course, we have, like I said, a variety of different fuels as well. So these are all chemical fuels. And that's what we use today for space travel. That is very primitive. If I was an alien who travels across galaxies, I would laugh at these primitive little monkeys who are using chemical rockets. What would advanced aliens use, for example? Well, if I were to speculate, I would say that they would use the reaction of matter and antimatter together. So antimatter and matter, if you bring them together, they just annihilate and give off pure energy, vast amounts of energy. E equals mc squared, right? So I think that could, if you can actually harness matter and antimatter, bring them together in a controlled manner, if you can store antimatter in a way that doesn't annihilate it, so that will require very advanced technology, way beyond anything that we have. First of all, we don't even have the means of producing any reasonable amount of antimatter. The most amount of antimatter we can produce or store is just maybe microgram or something, milligrams perhaps. And to store antimatter, we need magnetic confinement. So, advanced technology, if aliens have that, they would be able to store maybe kilos or hundreds of kilos of antimatter and matter together, maybe anti-hydrogen and regular hydrogen, and then bring them together to react in a combustion chamber and give off pure energy. And that would be an excellent way, excellent fuel for traveling interstellar distances, intergalactic distances, perhaps. But even that would not allow you to breach the speed of light, obviously, because of relativity, because of the laws of physics. So the other thing is we could possibly in the future have warp drives. So that may actually be feasible, um, possibly, but that is very, very speculative and futuristic technology. But it may be possible within the laws of physics. It may be allowed. So these are some things. So what is warp drives? You actually warp the fabric of space-time itself, and that impels you through space-time, possibly at speeds that exceed the speed of light. But because you are inside a certain bubble of space-time, which itself is moving through the larger fabric of space-time, that's why you're not technically breaking the laws of physics, that sort of thing. So that may happen, maybe if we stick around for another 1,000 years, maybe shorter, hopefully. Let's see. So that's a bit of speculation about space travel. More quantum. Dhruv says, can you discuss quantum entanglement and what are the current theories on how this phenomenon happens? Quantum entanglement, spooky action at a distance. Einstein, Rosen, and Rosenberg, who was it? Einstein and two of his minions, students, collaborators. So they came up with this very interesting idea, and it's valid. So what is it? What is quantum entanglement? I can best explain this using an analogy. Let's say I have a pair of gloves. You know what's a glove? You wear it on your hands, right? Let's say I have a pair of gloves. So what I'm going to do, I take this pair of gloves, I put it on the desk, I close my eyes, and I shuffle them around without looking, okay? Then I take one glove and put it in a box A, take the other glove and put it in the box B without looking at which glove it is. My eyes are closed. And I close the boxes, box A and box B, and seal them. Now, box A, I send it to Berlin. And box B, I send it to Bangalore. I don't know which glove has gone into box B to Bangalore and which glove has gone to Berlin. Now, my friend in Berlin opens the box and sees that it's a left-handed glove inside. Then my friend in Berlin will instantaneously know that what has gone to Bangalore is a right-handed glove corresponding to the left-handed partner that he has got or she has got, right? That is one way of looking at quantum entanglement. So now let's take this analogy and put it into and apply it to quantum mechanics. Quantum mechanics is all about the subatomic world, the hyper microscopic world. Let's say you have a subatomic particle with spin 0. Let's not go into what spin is. Particles have spin. Let's say spin is a property of a particle. Spin up and spin down are the two allowed states of this quantum number of spin. You can either have spin up or spin down, but a composite particle may have spin 0. Okay, so let's say I have a composite particle, quantum particle, which spontaneously disintegrates into two daughter particles. So my spin 0 particle breaks into two particles. Now this daughter particle A has spin up and daughter particle B has spin down. And if you bring them again together, they will have spin 0 because up and down add up to 0. So my quantum particle breaks into two particles, daughter particles, spin up and spin down. Particle A goes to Alpha Centauri, our neighboring star, Proxima Centauri, our neighboring star. That's particle A with spin up. And particle B with spin down goes to the Andromeda galaxy, 2.5 million light years away. Now my alien friend in Andromeda is going to detect the particle, and he or she or it will see it's a spin 0 or spin down. And then, even though he or it is 2.5 million light years away from particle A, which has spin up, he will instantaneously know by measuring one particle what the state of the other particle is. This seems to break the speed of light, because for information to travel from 2.5 million light years away would take a time period of 2.5 million years. And yet, the alien friend of mine in Andromeda knows instantaneously what the particle at the other end of that distance is. So that is an entangled system. An entangled system, from the quantum mechanical definition, is a composite system of, of two or more particles that has the same wave function. So this system of particles can be described. To describe the system of particles, you need a single wave function, and they are intrinsically entangled together. There is no way of describing one particle without also describing the other particle. That's one way of putting it. The best way of doing it is through equations, but I don't want to do that because it won't make sense to you. So that's what it is. It's a system that whose properties are entangled together. So if you detect and measure one particle and see what state it is in, you will immediately know what the state of the other particle is. And this is something that has been tested over kilometers. You have satellites in orbit that are able to test and validate that entanglement does happen at large distances. So that is what quantum entanglement is, and that's how it happens in well, roughly, approximately. Right. Animish says, what is your take on some mystery spots that claim to defy gravity? There are 3-4 places in the US and a few more in Russia. Are these artificially created with optical illusion, or can there actually be some effect of high magnetic fields and gravitational force? Gravitation and the magnetic force are totally separate. Magnetism has no effect on gravity. Now, yeah, there are these places called Magnetic Hill or whatever, even in India, right? Somewhere in northern India, in Ladakh or something, there is a place called Magnetic Hill where vehicles apparently go upwards instead of down and all that. These are nothing but optical illusions. None of these can be proven scientifically to defy gravity. It's nice illusions that you see. It all depends on the camera angle. You angle the camera in a certain way, things will look like they're going up. So that's what it is. And sometimes, even if you're there in person, based on where you're standing and all that, it may look like things are going up, even if you have switched off the motor or whatever. It's just illusions. There is no such thing as the effect of magnetism on gravity. Magnetic fields do not affect the gravitational force. Gravitation is not a force, it's geometrodynamics. It's the effect of mass on space-time and vice versa. So the presence of mass tells space-time how to curve, and the curvature of space-time tells mass how to move. That is general relativity, and that is what we perceive, this curvature of space-time. This curvature of 4-dimensional space-time that we are enmeshed in, that's what we perceive as the force of gravity. So there are no mystery spots that really defy gravity. They appear to because of optical illusions and all that. Nothing else. Nothing more than that. Suga says, do the laws of physics remain the same in the entire universe, or do they change from galaxy to galaxy? Well, I have only seen what I can see from my perspective on this little rock in my galaxy. All the data that we have is from our vantage point here on this planet in our galaxy. And from all the data that we have collected over all the centuries and whatever, the laws of physics seem to be the same everywhere. So that is the brief answer. From science is about data. It's about observations. And from all the observations that we have, the laws of physics seem to remain the same in all directions and all distances. There is your answer, sir. Christoph Frickschon says, in one of the previous episodes, you mentioned that you only have one meal per day, all you can eat style. What is the science behind that? Is it actually a good idea to mix carbs with protein? I heard it's not ideal to eat fruit with dairy. milk or legumes, for instance, wouldn't it be better to have a break between eating different kinds of food? Okay. First of all, is there any? Yeah, I do eat typically one meal a day. When I'm traveling, etc., it's not always possible to do that. But when I'm not traveling, when I'm at home, when I can control things, I prefer to eat one meal a day, all you can eat style. So one massive meal and that's it, done. Then forget about food. One meal. Uh, what's the science behind this? It's not typically all about science. It's about what works best for you. You have to observe your body. You have to observe the. I have tried 6 meals a day, micro meals. I have tried intermittent fasting. I've tried all kinds of things, and I found that what works best for me, for my physiology, for my DNA, for my metabolism, is one meal a day. It works good for me. I don't gain weight. I gain a reasonable amount of muscle when I'm working out and all. So that works for me. It may not work for you. It may not work for person X. It may work even better than me for person Y. It depends. Everybody is different. We are all unique human beings. Now, is it a good idea to mix carbs and protein? Is it not better to eat fruit separately and dairy separately and this separately and that separately? Look, we are anatomically, genetically, the same as our ancestors who lived 100,000 years ago, 1 lakh years ago. 100,000 years ago, our ancestors were most likely hunter gatherers. When you are a hunter gatherer, you hunt, and if you're lucky, you you kill some animal, rabbit, or a giraffe, or whatever it is. And when you do that, you and your family, or you and your tribe, your community, enjoy a big meal. Then is go back to basics, go back to hunting. You may go several days without getting lucky in your hunt. Those days you don't eat. Sometimes you may find some fruits, you may find some root vegetables, whatever. That was the hunter gatherer lifestyle. That is still encoded in our DNA. We have not changed. 100,000 years is not enough for evolution to make itself known. So the human species, Homo sapiens, has been the same for at least a quarter of a million years, 250,000 years ago, 2.5 lakh years. Anatomically the same, genetically also more or less the same. We have not changed much in that time. So all of that lifestyle, the hunter gatherer feasting and fasting lifestyle, is still encoded in our DNA. So when our ancestors would hunt, they would feast, they would eat carbs, they would, if they found fruits, whatever they found, they would eat at the same time. There were no refrigerators at the time. There was no storage. There was no agriculture, no grain storage. So you found a few potatoes, you found a few onions, and you found a rabbit. You ate all of that at the same time, and it worked perfectly fine for us. So all of this newfangled so-called science, bro science, that you should eat fruit separately, don't mix carbs and fats, or don't mix carbs and protein, all of that stuff doesn't make sense. Whatever lifestyle was our ancestors used to follow, we can still follow it today and be in good health. One of the best rules of thumb when it comes to deciding what to eat is to ask yourself a simple question. Did our ancestors, did forget about ancestors, did human beings eat this 1,000 years ago? You go to McDonald's, whatever you find there, nobody ate that 1,000 years ago. So don't eat that. It's unhealthy. You go to a pizzeria. Did anybody eat pizza with all the toppings and all that 1,000 years ago? No, nobody did. So don't eat that. It's not healthy for you. Some people like to drink wine. Yeah, wine has been around for thousands of years. So yeah, you can drink a little bit as long as you don't drink in excess. So the simple rule of thumb is, if they did not eat it 1,000 years ago, don't eat it today. It's not healthy for you. All of this processed food, all that stuff that people eat these days, that's why you have this obesity epidemic, diabetes, coronary heart disease, and God knows what other things. It's all because of processed food and all that. If you can cut that out, eat unprocessed foods, lots of vegetables, whatever protein works for you, etc., you will be just fine. So that's what I can say from my personal experience. Right. Alpha beta is lucky today. What is sleeping paralysis? Paralysis, is it related to horror or paranormal? Is there any permanent cure? It's called sleep paralysis. It's a, I don't know what. So it is something many people experience apparently, in which you are asleep and then you wake up, but you are paralyzed. You are not able to move, and you feel like there is some supernatural presence in the dark room that you are in the middle of the night typically, and you feel that there is something sitting on your chest, something heavy, and you are unable to breathe. So it feels like there's some demon or something sitting on your chest. You can't move your muscles, you can't open your eyes, and it's frightening. And this is something that people experience, many people apparently experience at least once in their life. So that is a phenomenon called sleep paralysis. It seems to be some sort of neurological or psychological phenomenon. It's something that is known to happen. So it is nothing to do with horror or paranormal stuff or whatever, because those things that well, have you ever seen a ghost? So the thing is this: it seems to be a neurological or psychological phenomenon. Ghosts don't exist from this perspective of science, because you can't take a photograph of a ghost. You can't replicate the phenomenon of ghosts and paranormal. So let's keep that out of the image now. So that is what sleep paralysis is. It is a frightening thing, I believe. People who experience this find it a very scary, frightening experience. They feel like, yeah, we have experienced the paranormal, the supernatural. We've experienced a ghost or a demon or something. That's what they feel like. Uh, I don't know about permanent cures or anything, or if even if there is any cure. I think it happens to people who sleep on their back. So typically, when you're sleeping on your back, you feel that there is something sitting on your chest, right here. So possibly one of the cures would be one of the, if somebody experiences this on a regular basis, maybe you can sleep on your side instead of sleeping on your back, or sleep on your face, on the stomach. So maybe that could help. So that's what I can say about this thing. Arman says, how can an average person who doesn't have scientific training tell if a research paper is credible or not? There is no way to sugarcoat this. A person who doesn't have scientific training cannot tell if a research paper is credible or not. The only thing you can do if you don't have scientific training is to rely on the opinions of people who do have scientific training. But then it is like second hand opinion that you're imbibing. So when you are relying on opinions, you're always opinions are always unreliable. Many scientists have opinions that have turned out to be completely wrong, and many scientific papers, high quality scientific papers. So one of the criteria that people typically use as a benchmark is to see whether a scientific paper has been published in a peer reviewed journal. So that is one benchmark. The second benchmark is, does it have lots of citations? Do lots of other scientists cite that paper? In that case, it is very credible, right? And some scientific papers are not published in peer reviewed journals. Some scientific papers are just left out there as preprints. There is this very famous preprint server called archive arxiv.org, which is the preprint repository for the physical sciences, for computer science, mathematics, and so on and so forth. You know what? When the very famous mathematician Grigory Perelman came up with his proof of the Poincaré conjecture, he wrote it down in a paper, in the form of a paper, and he simply placed it on the preprint archive. He did not submit it for publication to any peer-reviewed paper, to any peer-reviewed journal. So his groundbreaking proof of the Poincaré conjecture was placed on a preprint server, and it was not peer-reviewed. So that's also what you get. So it doesn't mean that if somebody has simply put their research on a preprint server, it doesn't mean it's not credible. One of the greatest mathematical breakthroughs of all time was never peer reviewed. And what happened after that is that a bunch of Chinese scientists tried to steal that and tried to take the credit for the solving of the Poincare conjecture. They tried to steal credit from Gregory Perelman. So that's what happened. So at the end of the day, there is no way for person without scientific training to really tell whether a research paper is credible or not. But there are these benchmarks that you can follow, and that would give you a good idea of how good or bad a paper may be. If it is published, that's a good sign. If it has lots of citations, it's an even better sign. So that's how you can possibly guess whether it's credible or not. Okay, this is big. Aditya says, I have recently joined the IIT JEE Coaching Institute in the 10th standard. I had simple topics like linear, quadratic equations, linear equations, Pythagoras theorem, various progressions, and so on. I was good at math. I used to get 80 out of 80 marks. But on the first day of coaching, they taught us differential and integral calculus. I found it very difficult. dy dx, d squared y by dx squared. My confidence has suddenly gone down. I used to be a topper, but now I'm feeling that I'll become the lowermost student of math. The same thing is happening for chemistry, physics, etc. Please guide me and how to do study of chemistry. Look, the first time somebody encounters calculus, it's like you're suddenly thrown into the ocean. It's so different from everything you've been taught before. Differentiation, integration, differential equations, and so on and so forth. It's like scary the first time you encounter it. It's like your whole world, whatever you thought was the reality, all of it has suddenly turned out to be illusion. That's how you typically feel the first time you encounter calculus. Differentiation, integration, and so on. Typically, one finds integration harder than differentiation because it's the opposite of that, and it's got a whole toolkit of techniques that one must learn. So what do? Simple. Solve problems. Take a book of problems of calculus. First of all, what you do, the first thing you do is you try and understand the concepts. What is differentiation? What do you mean by dy by dx? What are limits? Get these basics right. Talk to a good teacher if you have one, or acquire a good book. The Shom series books on pre-calculus, calculus are excellent. They're excellent for self-study. So first, understand these concepts properly. There are lots of YouTube videos which I believe would give excellent expositions on these basic concepts. So first, get the concepts right. Geometrically, what does dy by dx mean? What does an integral mean from the geometric perspective? Understand that. Get the concept right. Then, what you do is you solve problems. Not 2 problems, not 12 problems. You solve hundreds and hundreds of problems. You go through it. You force yourself for days, weeks, months. Give yourself 3 months. Just solve 100 problems per day. Maybe more if you have the time. Go through it. Do it again and again and again until it becomes second nature. You do this, I guarantee you, it will become the easiest thing in the world. Differentiation. Then the same thing for integration. Solve hundreds of problems, 100 problems a day. Solve 100 integrals per day. Do it for 3 months. See what happens. Your confidence at the end of those 3 months will be sky high. Same for differential equations and everything else. You have to put in the hard work. There is no substitute for hard work. You have to put in the hundreds of hours and you will solve the thousands of problems. You do that, I guarantee that you will become the topper again. And the same goes for chemistry. You have to solve problems, get the concepts, the fundamentals right. You have to be crystal clear about the fundamentals and then solve hundreds of problems. To be a good student, to be good at anything in life, you have to put in the hard work. There is no substitute for hard work. Talent is overrated. Talent means nothing. You may be the most gifted and intelligent person, but if you will not put in the hard work, you will achieve nothing. So that's what I would tell you. All the best, sir. Aditya. Okay, AK View is from Mumbai. I love science, especially physics, aerospace, etc. I'm very passionate about science, but recently I scored only 57% in the 12th boards. I cannot understand why. I can't do better in exams. I don't like rote learning. Over the years, my whole YouTube feed consists of lectures from Brian Greene, Lawrence Krauss, Michio Kaku, Feynman, and your videos, my videos. Even being so passionate about it, I cannot score in the subjects. Should I leave science, as I've been told by many, or should I stick to it as it's my passion? I would say that when it comes to passing exams, it's again about going through the process of solving hundreds of problems. Rote learning is a pain, I know. But in the Indian education system, you want to get good marks, you may have to indulge in some rote learning. So once again, the solution, the answer is the same. There is no substitute for hard work. You have to solve hundreds of problems. You have to put in hundreds, you have to solve thousands of problems. You have to put in hundreds of hours of hard work, effort. You do that, you will become good at anything. But of course, it's also about aptitude. You may love science, you may be passionate about it, but maybe for whatever reason, you may be better at something else in actual practice as a practitioner. Some people love music, but they can never play good music, right? It doesn't mean that they should not enjoy music, but it means that they should enjoy music as a hobby, as a listener, as a consumer. But as a practitioner, they should pick up some other career. That is also a possibility. So you may be somebody who loves science, who's passionate about it. Pursue that as a hobby, pursue that as a consumer of content, but maybe as a practitioner, you may be better at some other occupation. That is also a possibility. So try approach A first, do the hard work, solve hundreds, thousands of problems, put in the dedication and the effort for 3 to 6 months and see what the results are. And if you still don't find any improvement in your marks, then maybe you should take up after doing this experiment. If it still doesn't work, then maybe you should take up something else. So give yourself a chance first and put in the hard work. And if you still feel that you're not doing well enough, then maybe you can pursue science as a hobby and take up some other occupation. Okay, so that's what I can say. Plan A, plan B. Have both plans ready. Okay, let's take a couple more questions. This is by Samhita. Is microbial life present on Mars? Does that somehow give a hint of possible existence of life on Mars millions of years ago? So we don't have unambiguous evidence of microbial life having existed on Mars. We have a piece of rock. I forgot what it's called, ALH something something something. We know it came from Mars, and a cross section of this rock was taken and microscopic analysis was done, and what was detected is microtubules that look exactly like the capsules of bacteria on Earth. So if it is indeed the fossilized remains of ancient bacteria, then it means that in the past there used to be bacteria on Mars. Maybe even today they may have survived underground, possibly. So it's a possibility, but it's not 100% proven. Some people say it's just a coincidence. Some scientists say it could be just a coincidence. It is not an unambiguous demonstration that this represents ancient life or a sign of ancient life. Apart from that, we have the Americans, NASA has a rover, I forgot what it's called, Perseverance, Ingenuity, Endurance, whatever it's called. So it's doing some research there. There's a helicopter also over there, a small rotorcraft. So, but that's not quite equipped to look for signs of life. It's doing various kinds of scientific tests on the atmosphere and the soil and the composition of rocks and all that, but that's not enough to tell us for sure whether life existed or not. We do know that a couple of billion years ago there was flowing water on Mars. Mars was a much hotter place. It had a much thicker atmosphere. It had a magnetic field. And it's quite likely, not likely, it's quite possible. It is not quite possible, it is possible that life may have existed on Mars at that time, when it was a nice, warm planet with a thicker atmosphere and flowing water. It's possible. So the possibility is very much there, but the evidence still is not there with us. At least unambiguous evidence, we don't have that. Right? So that's the answer. The logical motivation 95 says, Can you explain the spaghetti effect in detail and in normal English, please? Well, that's what I strive to do. I strive to explain things in normal language. So, have you seen Saturn? So, what you're talking about, the spaghetti effect, is called spaghettification. It is something that is related to black holes. So, let me explain this. We know the very famous iconic planet called Saturn. Saturn has rings. It's a planet, a gas giant with a massive ring system around it. Why do those rings exist? Those rings are the debris, the rubble that comes out of an ancient moon of Saturn that was destroyed maybe in a collision or something else. Now, in physics, in classical Newtonian physics, there is something called the Roche limit, Roche, Roche limit, and the Roche effect. That has something to do with tidal forces. So every every object, every planet has a Roche limit. So this limit is the limit at which, if any orbiting object comes within that limit, it is going to be ripped apart by tidal forces, and it won't be able to stay in one piece. Roughly, that's what it means. Roughly, okay. Not this is not the precise definition, but if the moon, for instance, if the Earth's moon were to come closer to the Earth, this is the Earth, this is the moon. If we were to move the moon much closer and bring it within the Roche limit, then the moon would be disintegrated by the tidal force of the Earth. What does tidal force mean? It means the Earth is here, and let's say this is a satellite. The pull of gravity on the part of the object that is closer to the Earth is way greater than the pull of gravity on the other part, and that distorts and destroys the object. That is the tidal force at the Roche limit, and within that. So, in the case of a black hole, the force of gravity as you go closer to a black hole is way, way, way stronger. Black holes have incredibly strong gravity. So as you come closer and closer to the event horizon of a black hole, the tidal force becomes larger. So let's say you're a human being. Let's say this is a human being going towards a black hole. The bottom of the screen is towards a black hole. You're going closer and closer. And as you go closer to the black hole, the force of gravity on the legs is way greater than the force of gravity on the head of the person. And we know what that does. It'll pull that person and stretch that person apart like strands of spaghetti. So that is spaghettification. And as you cross the event horizon and go towards the singularity, which may be there inside, the tidal force gets even stronger. So if it is a reasonably small black hole, the spaghettification is much larger, much stronger, and the tidal forces are much greater. If it's a supermassive black hole, you may not experience that drastic spaghetti effect. So that, in short, in brief, in normal English, is spaghettification. It's that a person who is falling into a black hole, feet first or head first, will be pulled apart as if they are spaghetti. Not a good way to go, right? So that is the spaghetti effect. All right, I am done with today's questions. Shall I take a couple of live chat questions? Okay. Can we drink alcohol in black hole? Well, if you can get inside a black hole with your bottle of alcohol, you can try it. Okay, what else do we have? Let's take a couple of questions, if we can. You have some questions. I'll take a couple now. ISRO Venus mission. I have heard of some mission that ISRO is supposed to undertake to Venus. Shukrayan, is it called? I'm not sure. So I don't know the details. I don't know which year it's going to happen. Maybe by 2025 or something. That's what I had heard a couple of years ago. So typically, what one would imagine is that you would send a spacecraft to this planet, to our neighboring planet Venus. The spacecraft would go into orbit around Venus, and it would have a bunch of scientific instruments that would do various tests and analysis of the atmosphere and maybe the surface of the planet. So if you send a spacecraft that has a radar, with it, then you can maybe do a radar scan of the surface of the planet and get details about its topology. And if you have spectrometers and other things, then you can look at the composition of the gases of the atmosphere and gain more knowledge about that. So that's the kind of thing you could do in a Venus mission, and that's possibly what the Shukrayan mission will be about. But I'm not sure when it's going to be launched, and so that is still something that needs to be looked at. All right. You would take the diet question, but not mine. You are a typical Indian. I am a typical Indian, sir, but I don't know what your other question is. Instead of asking this question or making this comment, you could have asked your question again. I get thousands of comments. I cannot pick everybody's question. Please understand that, please. Okay, what else do we have? Okay, some people are asking questions about things that are not related to science. Please don't do that. Today is about science. This live stream is only about science. When is the Earth going to be destroyed? The Earth will be destroyed when our sun becomes a red giant. So, in roughly about 5 billion years from today, the sun will become larger and larger. It will have become a red giant, and eventually it will shed its outer layers, and that will go out in the form of a nebula, a planetary nebula, which may look kind of like the cat's eye nebula, perhaps. The sun is never going to go supernova. The sun is too small for that. So it will eventually shed its outer layers. It will first become a red giant. It may engulf the planet Mercury within itself when it becomes a red giant, and eventually the nuclear reaction within the sun at the core will become weaker, and the outer layers will be expelled slowly over time, and that could very much destroy the Earth. And even before that, when the sun becomes a red giant, the oceans will boil off, and whatever water is left on the planet will disappear. The planet Earth will become very hot and dry. So that's the kind of destruction our planet will see. Eventually, the sun will become a white dwarf and spend its remaining days like that. So that is the kind of fate, eventual long-term fate our planet will see. Okay. What is Murphy's law? Is it purely hypothetical? Murphy's law is not science. Murphy's law says that if something can go wrong, it will go wrong. It's not science. It's just it's kind of a joke, actually. It's not a joke, actually. It's quite painful. People experience that, but it is not science. It is a certain pattern that one sees in life sometimes, that if something can go wrong, it probably will go wrong unless you have taken the best of precautions. So that is what Murphy's law is, and that's where we are. Do I believe in ghosts? Well, I have not seen a ghost, so unless I see one, how do I believe in it? Yeah, but I don't know if, ghosts are something you can't prove or disprove. So that's not science, it's philosophy or spirituality or whatever. All right, I think we are at the end of today's session. Almost 2 hours. So we'll end it here. Thank you, everybody. Great to be talking science again. That's what I find the most interesting. I'm a science guy more than a history guy or a geopolitics guy or whatever else guy. Science is what I enjoy the most. So it was great to do this again, and we'll do it again in the future. Thank you, everybody, for your questions. Thank you for watching. Thank you for your viewership. And once again, this video was sponsored by the like button. Go and smash it and thank our sponsors. Thank you very much. And I will see you in the next live stream, which is tomorrow. Bye.